In this video, I'm going to talk about nodal analysis. So to know about nodal analysis, first we need to know KCL. KCL is nothing but Krichov's current law. Here, Krichov is a person's last name. He's a German scientist or physicist. He developed this Krichov's current law in 1845. So according to Krichov's law, current law, at any junction, a junction is nothing but where two or more wires connected together. Okay, so at any junction, currents coming in must be equal to currents going out. So sum of the currents coming in. So here I have I1 coming in, so I1 must be equal to sum of I2, I3 plus I4. This is Krichov's current law. So basically you're not storing any energy, or there is no current drop at a junction. Whatever current entering in is leaving out through the other paths. It's just like water flowing in. You can analyze it with the water. Whatever water is coming in here, that water must leave through different paths. So it is leaving through different paths. This is similar to the water flow. It's called Krichov's current law. Now here we are learning about nodal analysis. Okay, so what is nodal analysis? What is the necessity? Why do we need to do the nodal analysis? We already know how to do series parallel combination, star delta. Why should we learn this nodal analysis? So if you look at series parallel combination method or star delta method, there we used, there is only one source, but in reality you look at many circuits will have more than one source. So for example, if you take your radio is going to have two sources. One is power source, that is coming from the batteries. Another one is the signal, the audio signal. That audio, it is nothing but electromagnetic wave. That electromagnetic wave is coming from a radio station. That is another source. Okay, so there are two sources for the radio, two sources, two types of sources for the radio. So many circuits will have two or more than two sources. So if a circuit has more than two sources, then it is impossible to solve a circuit by using series parallel combination method. So to solve those circuits, we are using either mesh analysis, nodal analysis. Now I'm going to start with a simple example here. Here is a simple example. I have a 20-volt source and then connected 15 ohms, 20 ohms, 10 ohms. So here is a given example. Here I have two sources. One is a 20-volt voltage source, another one is a 5 ampere current source. What is the example for a 20-volt source? Probably I would say this is a battery. A battery is nothing but a voltage source. A current source, most probably you can say a solar panel is a current source. Solar panel is a current source. Now to solve, question might be like, find the current passing through this 20 ohm resistor, find that I2, whatever that value is, or IL, load current. Okay, find the current passing through the 20 ohm resistor. That's the given question. Now by using nodal analysis, what we're going to do here, we're going to find all the node voltages first. Okay, so once we find the node voltages, it's easy for us to find the current passing through this. So basically, say for example, I have a node voltage here. Let me label this as V2 and label this as V reference. Okay, so I can say my IL, as long as I know V2 and V reference, my IL is nothing but V2 minus V reference over 20. Okay, if I know all the node voltages, not only the current passing through this 20 ohms, I can find current in any resistor in this circuit. So step one, what I'm going to do here, so step one, find all the nodes in the circuit and label all the node voltages as VA, VB, VC, or V1, V2, V3, etc. So node is nothing but a junction where two or more elements connected. So here, is this a node? Yes, that's a node. I'm going to label that as V1. Is this a node? Yes, that's a node. Label that as V2. Another node, V3. Is this a node? Yes, that's a node. V4. Is this the same node or different node? This V4 and V reference, they are the same nodes because there is no element here. It's just a wire. It's a short circuit. Okay, since it's a short circuit, this V reference and V4, they both of them are the same nodes. Another way of defining this is nothing. I mean, can I connect this as like this? Okay, so you can see all the wires are connected at the same node. I can take that as V reference. Okay, now that's our step one. Step one is find all the nodes and label each node voltage as unknown node voltage, V1, V2, V3, and V reference, or V4, V5, something like that. I'm going to choose the bottom node as a V reference because in any electrical circuit, at one point, node voltage, at one node, the voltage is going to be 0. Okay, so here also in electrical circuit, what I'm going to do, I'm going to choose one node voltage as a reference node, and that node voltage is equal to 0. So choose one essential node as a reference node and assign that essential node voltage as 0. What is essential node and why I'm talking about essential node instead of a node? Essential node is nothing but where more than 2 elements connected. Okay, is this essential node? Yes. Is this essential node? Yes. This is essential. This is essential. All 4 nodes are essential nodes because where more than 2 elements connected. But it's a good idea to choose where more than 2 elements connected. Here only 3. Here I have 4. I have 4 here. 4 elements connected. 1, 2, 3, 4. So whichever has highest connections, choose that as a reference node. In that case, can I choose this as a reference? Sure, you can choose that as a reference. We both will end up with the same numbers. Okay, but I mean, for simplification purpose or easy purpose, I'm going to choose the bottom node as a reference node. Okay, so rest of my examples, I'm going to choose the bottom node as my reference node. Okay, now next step. So choose reference node voltage as 0 volts. Okay, this voltage as 0. We always choose one node voltage as 0 volts. That's called reference node. Now, one important point. Okay, I'm going to write it down. So here, if there is a voltage source, so step 1 you need to do to find if there is a voltage source between unknown node and reference node. So if there is a voltage source between unknown node and reference node, then that unknown node voltage will be equal to the source voltage. So here between V1 and V reference, I have source voltage. So basically, if you remember all the time, say here is an element, the voltage here is VA, voltage here is VB. What is the voltage here? VAB. How do you define VAB? VAB equal to VA minus VB, right? So similarly, if you look at this, I have a 20 volt. Okay, here I have 0 volt and here I have V1. So can I say, by using the same principle, can I say V1 minus 0 equal to 20 volt? So V1 equal to 20 volt. So here I have V1 equal to 20 volt. Now our main goal is finding IL. Okay, now I'm shifting my goal from finding IL to finding V1, V2, V3, because once I know this V2 minus V reference over 20 will give me IL. Okay, so I'm shifting my goal from finding IL to finding V2. Okay, once I find V2. So here I have 3 unknowns, so I need to end up with the 3 equations to find those 3 unknowns. But in this case, the first one, instead of equation, I directly got the final value of V1. V1 equal to 20 volts. Now at V2, apply KCL. Okay, so here at V2 there is no voltage source between V2 and V reference. At V3 there is no voltage source. This is a current source. Okay, I'm talking about the voltage source. So I have to apply KCL at V3. So at V2 apply KCL. Apply KCL. So here I'm going to choose all the currents are going out of that junction. So IA, IB, IC. Is it possible to have all the currents are going out? It is not possible. So for sure, remember, current is a vector quantity, so you can change the direction. So for example, if there is a 2 amperes flowing in this direction, you can say same thing, minus 2 amperes flowing in the opposite direction. So current is a vector quantity, it has magnitude and direction. So definitely out of these three currents, one of them must be a negative current. Okay, so I don't care about the negative current or positive current there. I'm going to choose every current is going out because my equation is going to be simple. So IA, so apply KCL at V2. So IA plus IB plus IC equal to 0. Now I'm going to write IA. IA equal to, can I write IA equal to, here is my IA. This voltage, current always flows from higher potential to lower potential. So V2 minus V1 over 15. So IA equal to V2 minus V1 over 15 plus, I know V1 equal to 20. I'm going to substitute it in a minute. And IB equal to V2 minus 0 over 20. So V2 minus V reference over 20. IC is nothing but V2 minus V3 over 5. V2 minus V3 over 5 equal to 0. Okay, this is my KCL, applying KCL. Okay, now V1 equal to 20 and V reference equal to 0. I chose all the currents are going out of this junction because you can clearly see everything is in terms of V2 minus something, V2 minus something, V2 minus something. So if you practice 4 or 5 examples in this manner, it's easy for you. You can close your eyes and write the equation. So that's the reason I'm choosing every current is going out of the junction. If you choose one current is coming in, another current is going out, say for example, here is the junction, same junction I'm talking about. Say if you chose I1 is coming in, I2 is going out, I3 is going out, you can choose I1 equal to I2 plus I3. We'll end up with the same thing. Okay, it's a same equation. Okay, now let me simplify this equation offline. So here V2, I substituted V1 equal to 20 and V reference equal to 0. So V2 minus 20 over 15, V2 minus 0 over 20, V2 minus V3 over 5 equal to 0. To eliminate the denominator, I'm multiplying this with 60. That's a common factor for this 15, 20, 60. So that's how I chose this number. Okay, so 4V2 minus 80, because 60 divided by 15, you will end up with 4 here. So 4V2 minus 80. 60 divided by 20, you will end up with 3. So 3V2 plus 12V2 minus 12V3 equal to 0. So 19V2 minus 19 minus 12V3 equal to 80. That's our first equation. Actually, I would say this is our second equation because we already have first equation as V1 equal to 20. So I'm going to take this as my first equation, V1 equal to 20. Now at V3, so if you look at V3, we have 4 nodes connected there and there is no voltage source between V3 and V reference. This is a current source, this is not a voltage source. Okay, so you need to apply KCL. If you have a voltage source, you don't need to apply KCL there. Okay, since it's a current source, at V3 apply KCL. At V3 apply KCL. Okay, so here also I'm going to choose every current is going out. I'm labeling them as I1 plus I2 plus I3 plus I4 equal to 0. Okay, so here every current is going out. I'm choosing this I1, I2, I3 and I4. Okay, so what is I1? I1 is nothing but V3 minus V2 over 5, and I2 equal to V3 minus 0 over 25. I4 equal to V3 minus V1 over 20. Now when it comes to I3, can I say I3 equal to negative 5 amperes? Because here is a current source, okay, 5 amperes. The 5 ampere current is flowing in this direction, but you're assuming I3 current is flowing in the opposite direction. So I can choose this I3 equal to negative 5 amperes. So at V3, I'm going to apply KCL, write down the equations. So when we apply KCL here, I1 is nothing but V3 minus V2 over 5 plus V3 minus V reference over 25. I3 is nothing but negative 5. Okay, don't get confused. This is, I mean, V over R is nothing but I. Okay, this is what this is: current I1, current I2, current I3, current I4. Okay, I'm adding current, so we're okay on that. So now eliminate the denominator by multiplying maybe 50. Okay, I'm going to do it off. So I substituted here V reference equal to 0 and V1 equal to 20. So I end up with another equation. This is my third equation. 17V3 minus 10V2 equal to 350. Now we have two unknowns, two equations. So one equation I have 19V2 minus 12V3 equal to 80 minus 10V2 plus 17V3 equal to 350. So I have two unknowns. So here minus 10V2 plus 17V3 equal to 350. This is my other equation. Now here two unknowns, two equations. Solve for those two unknowns. Okay, I'm multiplying equation 2 with 10. That's a coefficient of V2. I'm multiplying equation 3 with 19, which is coefficient of V2 in equation 2. So that way we can cancel out V2. So it's 190 V2 minus 120 V3 equal to 800 minus 190 V2 plus 19 times 17, which is 323 V3 equal to 19 times 350, 6615. Okay, now if I add these two equations, I will end up with 203 V3 equal to 7450. Okay, end up with V3 equal to 36.69 volt. Okay, once you substitute this V3 in equation 2 or equation 3, substitute V3 in equation 2, I end up with V2 equal to 27.38 volt. Okay, once I find V2, I can find any quantity. I mean, since I know every node voltage here, I can find any other quantity, but our goal is finding IL. Your IL equal to V2 minus V reference over 20, so which is nothing but 27.38 over 20. That value is 1.369 ampere. This is our current passing through the 20 ohms. Sorry about for the long video. I'll try to minimize this length of these videos to 10-12 minutes in the future. Okay, since this is the first example, I need to go through many points. Thank you. I will post more videos on the nodal analysis.